I would like to welcome among us Dr. Bishnu Atal. I was thinking how to introduce him because if I were just naming all the awards which he got, I think that we would cut into his talk significantly. But he has the usual honors, Academy of Sciences, Academy of Engineering, Inventors Hall of Fame, and so on and so on. But I realized that probably the best introduction is that you realize that most of us actually carry a little bit of Bishnu in our pockets. Because if you take out your cell phone, I can guarantee you that a little bit of Bishnu is in each of these cell phones, namely linear prediction of speech, which now looks like a normal thing, just like Fourier transform and whatever. But when it was invented some 30 years ago, 40 years ago, 30 years ago, it wasn't.
He's not old enough to have done.
Yeah, it wasn't as obvious as it looks to us right now. And Bishnu got on the other things too. I mean, and he will tell us about that today. So please, Dr. Bishnu Atal.
And thank you, Hinek. I am very glad and I am really grateful for the university and the speech group here to invite me. When Hinek wrote to me that I should give a seminar here, I was thinking, well, who will go all the way from state of Washington to Maryland? But then I said I should learn more about the work being done here, and he's here. That is kind of a surprise because he was supposed to be in Switzerland. And I don't know how he landed up here, so I thought I will find out what he's doing there. On top of it, I was struggling with some problems in Fourier analysis, and I thought, that's it. Where else I can get so much help? You know, I don't work at Bell Labs anymore, and for every little thing I have to run around. And here at one place, all the knowledge is here. So I'm going to talk about this topic, which is an old topic, and you wonder, what is this Fourier analysis business going on? Why are you working on this topic? What is this long settled thing? Is no longer an issue, anything. And probably this is true. You know, when I joined Bell Lab in 1961, Fourier analysis was a hot topic then. Blackman and Tukey had just published their monograph in BSTJ in '58. And Fourier analysis was not a thing which was common. It used to be very expensive to do any Fourier analysis. Computers were just coming, they were slow, and Fourier analysis takes a long time to compute. But when Blackman and Tukey did some Fourier analysis on not on a speech, but on some data from AT&T, they found a lot of unwanted phenomena there because Fourier transforms are defined on a long record of what I call infinite length. But we live in real world where nothing is infinite, and if you have a finite record, no matter how long it is, it creates problem if you do a Fourier analysis due to minus t to plus t doesn't do things right. And a lot of other problems. If you ever put white noise into this integral, all more problems come in. So they put their wisdom in. They said we should use tapered windows. They discussed number of windows, and Hamming window was one of them. And it became Hamming window became, for speech people, adopted window. Everywhere Hamming window is there. But Fourier analysis was not common. Most of analysis those days was done on sound spectrograph machines, which used wideband analysis, narrowband analysis, and so on, so on. Ultimately, Tukey and Cooley introduced the fast Fourier transforms, and that kept us busy for several years, and we learned about them, and we got busy using them. Computers are still very slow, and Fred, of course, was not at IBM at those days, but IBM 1799, which was the fastest computer, was an order of magnitude slower than little things you see around here. But that's how the world was. I got diverted towards linear prediction in those days in '66 and never worried about windows because I thought that's the problem of these people, of Fourier people. That's not my problem. I kind of forgot all about it. And in fact, the papers I wrote in linear prediction did a analysis of a rectangular window. And I thought I'm smart because I use the covariance method and kind of claim that problem of window doesn't bother me. Well, it went on. Of course, some other people use, again, Hamming window and compute autocorrelation, and that went on. But later on in 90s, I discovered that I was fooling around. The window did an effect because once I plotted, in a speech, we never did everything, every speech sample. We did every 10 milliseconds. But once I did plot all LPC coefficient every speech sample, and I was horrified to see that, what I was doing, because everything was jumping up and down, and near a pitch period, it will go through a sharp peak for no purpose, and nothing in vocal tract happens that way. And I was claiming LPC coefficients are related to vocal tract, but that phenomena has nothing to do with vocal tract. So I backed out and said, okay, I did some correction, wrote some papers about how to get rid of some of these problems, but never. So window was an important part. And it went on until I visited OGI, and somewhere in 90s, I don't know what my first visit, maybe 94 or 93, and Hynek said, this 10 and 20 millisecond window are no good. You should use windows like quarter, half, 1, longer, and so on, so on. I didn't understand why he's saying that, but I was busy in other things. I listened to it and say one day I will like to understand that, but I forgot all about it. Until in 2002, I joined University of Washington, and I started working with Professor Atlas there. He had visited Hynek earlier, and Hynek has put him on the track of long windows. So he was using a long window for some of his work, and saying it's good, but no one explained to me why is it good, why should use long windows. After all, in speech, long window was considered bad. It kind of averages too many things here and there. Of course, Professor Atlas's work was in modulation. He has a model of signals, including speech and music, what he calls a carrier modulation product model. That is, there is a set of carriers. He divides the whole frequency range into a set of subbands. And each subband, he thinks there is a carrier there. And a carrier is multiplied by a modulation signal. And the question is, what is the carrier, what is the modulation? And he was himself inspired by some of the comments made by Homer Dudley in 1939, because Homer Dudley in his thinking was saying, that was the philosophy of his vocoders. He said in his speech, there is a carrier which is high frequencies, and Dudley's thinking, carrier is like vocal cord and glottis and all those kind of things. And the vocal tract produces modulations, which are much slower frequencies. And that was his basis for telling AT&T that we can compress a speech to 300 hertz bandwidth rather than 3 kilohertz. So he, in fact, wrote that. And Les Atlas was trying to kind of make that a reality. And that's a topic which still he's busy with, because it's a difficult topic. What is the carrier frequencies? Someone may say, first he thought instantaneous frequency obtained by some method may be the right solution. But a lot of problem instantaneous frequency, if you see the math of that. Then he went to a frequency reassignment. There are a lot of papers on frequency reassignment in the time frequency plane. Well, he did that, and that again, a lot of problems. Then someone said, well, use the pitch harmonics as the frequencies. Well, you got another set of problems. And you can work all your life on any one of these methods and never get anywhere, because, as you know, pitch is not a new topic. People have spent life on finding pitch. And I had experience with pitch that I keep away from this, because I spent decades on this, and until I got rid of pitch, the speech coding was a dead horse kind of thing. Nothing will come out until I went to multi-pulse LPC, which has no pitch, and everything works. So pitch doesn't work. And then he read somewhere else, and then he's trying now some center of gravity kind of thing, and so on, so on. This will continue forever. But there is an interesting model, and he is busy, and we are getting very interesting results. But I have a simpler problem, and I will, apart from the history I gave, I will like to kind of share with you my difficulties. And please feel free to comment and give your wisdom on this simple topic, which is a little mystery to me. So we go to the first slide, and this all is very familiar thing, nothing very new here. Fourier transform, the way it starts, is non-useful for us. What someone really introduced the idea of some kind of a window which is running in time. And that's a very useful concept. So anytime t you want to look at a speech signal, you look through a window. And this is very intuitive. You know, we always want to see something closely, we just look through a small hole. You look through that window, and in this case, if I am right here, this window is at time t, and a speech signal, of course, goes forever, and you only look at this part of the signal. And I have put a Hamming window here. And if you convert this picture into a mathematical form, it gives you the definition of short time Fourier transform, which we all familiar use all the time. It looks so simple, but introduction of window creates complications. So let's go to, in this case, the window is t seconds long. But let me go to the next picture. Okay, let me go first before. What I see here, this is, you can look at this integral, or you can say this is this function of time, s tau e to the power minus j omega tau, converted to a new variable tau, convolved with h of t. That's a perfectly legitimate way of looking at Fourier transform. You never have to use the word even window from then onwards, because you are convolving a signal multiplied by a complex signal e to the power minus j omega t, convolved with another time function h of t. And on the next view graph, I did this. S of t multiplied by e to the power minus j omega t, convolved in time with a filter h of t, giving you a function of time t and a function of frequency. And you can do a lot of things. Now, st of omega are not here variables where you could put any two-dimensional function and get anything meaningful out. They are dependent things. But by integrating properly, you can get the time function back, and a lot of work has been done on this kind of things. But st of omega is an interesting function, is a function of at any omega. Suppose you say, I want to look at only one omega here. This gives you a function of time. And that view comes closer to what Hynek has been saying. Whether we call modulation or not doesn't matter. There is a time function s of t, and a big S, which we want to understand. Does it have any... In speech, we always concentrate as a function of omega. That's our preoccupation. We feel that is the central quantity. Let's look at that, study that, and we have done a lot of work on that. But looking at any one frequency, a function of s of t, very little diversity is there. I had to read a lot of OGI, but I am suspicious of all that because that comes from Hynek. So it's all one, one view of the world, which I can't trust. And there's not that much available as a function of s of t. What is this s of t thing? Is it useful? What can I do with that? So I just drew a picture of, I'm sorry, no. This mathematics I have put there into a form, and I like this form of Fourier transform, or short time Fourier transform. It's so simple. Take s of t, shift the frequency to anywhere where you like. It's almost like through a microscope. You take a microscope and start looking and say, oh, I want to look very closely here. And you can. By doing that, because now at omega is DC here, at 0 frequencies. And the linear filter determines what range of frequencies you are looking at. If I want to look at 1 hertz, I can look at 1 hertz. I put a filter with a bandwidth of 1 hertz. If I want to look 100 hertz, I put a filter of bandwidth of 100 hertz here. Now question comes, what should h of t be? I cannot use the same argument which Blackman and Tukey used to determine h of t. Their argument was spectral analysis as a function of frequencies, and they got all these ripples and Gibbs phenomena and all this. I'm not looking into that. I want to know, should h of t should be very sharp. In filter technology, we talk of how many dB per octave the slope be after in the filter on the left or right hand side. I can't find any answer there. Should I use Hamming window? Maybe, maybe not. And we'll come to this question again later on. What should be the width of this filter, time width of this filter, symmetric, anti-symmetric, and what about the slope of the cutoffs? How sharp, how slow, what impact it will have, what I'm going to observe. I want to observe something about sounds here. That's my purpose here. Now people do one more operation here, which I didn't talk about, which add enormous complexity to all this discussion. They take a magnitude squared. Now I don't know where this comes from, but I already have difficulty resolving this issue here. When you take magnitude squared, it adds complication which will take me rest of my life to resolve. Why? Because this is a nonlinear operation. In nonlinear operation, we do it if somebody tells you do this transform and your life is simple. I don't know whether I can say about this magnitude square nonlinearity. Why do we do that? Not only that, if you have sum of two signals, and more I am finding we never in daily life encounter pure speech, clean, no noise, no nothing, just plain the way it is created at the lips. You don't see that. You see people talking together. You are cell phone user, you are speaking, but someone is talking at the same time. We have two signals. This nonlinear thing creates not just the sum, but a lot of cross products. And more terms you have, more cross products you have. Very soon you find you don't have what you want, you have a lot of unwanted phenomena. How to resolve that? Now, this is the form. It's certainly just repeat the same operation here, that I have st of omega, I take magnitude squared, I have this, and I am just saying what I said just now. Here, if you have multi-component signal, short-time Fourier transform is nice and elegant. You add 2. You take magnitude squared, you get, of course, magnitude squared of 2 plus a fringe benefit of this product. Now if I have 3, you get more. If I have 5, you get even more. I'm going to sort it out. What is what I want and what I don't want. And I read here, there, here, and not too many papers on sorting out all this thing. Ultimately, I want all this knowledge to some good use. Before I can get put to use, I have to resolve in my own mind what am I doing, and which I am lost. So let me take a breather of a minute or so and ask your wisdom. What's the advantage of using this magnitude squared? Why should I do that? Why not happy with STFT, which is all linear? I can, if you add two things, there is a hope, and if you have linearly, that I can do some filtering here and there and get it out. But if you add so many cross terms, how am I going to filter out? So let me go back now to the old magnitude squared. I said this, and I don't know the answer. So I'm keeping away from magnitude squared. This just, I can't understand this. Now, let me go back to this time, the window business. And a little short digression. When I visited Hinek, he already had described to me saying we should use long windows. But he had already introduced things like Rasta, which he was saying is better for certain conditions, especially with noise and reverberation and so on, and his work was itself inspired by some of the work done by Fourier In speech, for most of the time, we used to take a window of 20 milliseconds. Now, one more comment before I move on. Now, if I take this deals with this phenomena. If I have a signal and I put a window there in the previous one of time t, let's take for example a 20 millisecond window which is used. A 20 millisecond window has a 6 dB bandwidth of 100 hertz, two-sided, and 0 to 0 is 400 hertz. No, sorry. 20, 10 is 100 and 200. Now, if I take magnitude square, the bandwidth is increased 2 times, right? So, if I use a 20 millisecond window, how often I should compute this magnitude square? Sampling theorem says every 2.5 milliseconds. So, I consulted. There is not one single paper which does 2.5 millisecond spacing of windows. It's done 10 milliseconds. Where this 10 milliseconds come from, I don't know. Apart from all these distortions, it folds over all these high frequency distortion back to 0 frequencies. So this magnitude squared phenomena is so complex, that's why I said leave it alone. Maybe Hynek will resolve this one of these days. So what, we were doing this 20 millisecond analysis, but Furui pointed something very important at one stage. He said, and there's a context to his work, he said if you don't take just the parameters, and parameters in those days were Capstrom, you take a derivative of the Capstrom, and he called delta Capstrom, determined over 100 millisecond time window, and he said performance of speech recognition is improved. And that's where this paper of his shows error rate in his, whatever he was testing on, if you have Capstrom was close to 15. If you combine with these derivatives, it goes to 8-9%. And there is some difference, but not much, depending upon how many frames you use. And even if you don't use this, the frame Capstrom, but a delta Capstrom, they themselves are as good almost as the frame Capstrom. Difficult to understand in those days. We started using, we got so excited by that because it cut down the rate by a large amount from 15 to 8. Oh, and then we immediately said, let's get delta delta. It also brought it down further, and those things are now part and parcel of every speech recognizer without question. Because the advantage gain was so large compared to anything else we did, we adopted that without question. But question is why? Why delta Capstrom give an advantage, we don't understand. And of course, you read psychoacoustic literature, you can find some rationale for that, but nothing very satisfying. It's a mystery, but used all the time in our work. Now this I just borrowed.
It also directly violates the underlying model if you're doing a Markov process model.
Absolutely.
It's stationary in the...
Jim is perfect. It gives me a headache. Each time I start thinking, I give up. And I've done this over the last 25 years. I thought I will sort it out. The moment I do some half an hour of thinking, I give up and say, this is beyond my reasoning. But this is the one single parameter which is so useful. Why? Now, when I visited Hynek, he described to me, and I thought I could show you the starting point of my things. Oh, sorry. Okay. So what Hynek did and his co-workers, in this case Carlo, in 1997 they published, they take a small slice of the spectrum, magnitude square thing, and it goes up and down. And the question is, why does it go up and down? No one discusses that, because it should not go up and down. If the spectrum was such a good thing, why should it go up and down? We think no problem, if it goes up and down, we'll get rid of noise by filtering. So ST of omega k, just omega k is the same variable omega I had, and what she says, spectral analysis is another Fourier analysis, and you go into a new domain called theta. And Les Atlas like to call it now, we have 3 domains, time, acoustic frequency, and modulation frequency. And he had a lot of 3-dimensional plots of speech and all this. So there's, and a lot of literature which says modulation frequency and modulation index and modulation filtering, and a lot of work in that.
Just to make sure I'm connected to your talk. So the width of that red band has to do with the h of t that you had, I mean, depending on...
We'll come to that. That's a complicated question. This width is what Hynek said, maybe 100 hertz or so, is subband. Nothing to do with that filter. And we'll come back to this. It's good you raised the question. That's when my, after finishing that, we go around the circle and come back. This is 100 hertz filter here, and he puts another filter. There are 2 filters here. This filter is kind of very casual. The only 2 lines are discussed in every paper. Oh, I use either critical band filters or 100 hertz filter. There are 16 of them, and one doesn't pay too much attention. This kind of some normal operation in speech analysis. Essentially, this allows you to focus on some band of speech. And this is the envelope coming out of this here. How do you compute the envelope is not important, but you can, taking real and imaginary part and magnitude squaring, you get this envelope, what you call, he called trajectory. Now, so this shows now how. Well, S of t goes to a bank of bandpass filter of some width. It could be critically not linearly spaced. It could be non-uniformly spaced. Several filters, maybe 15, 20 of them. Each one of them creates some jiggly thing like that, the kth band. You pass through another filter here. And that is the filter Hynek says should be very narrow, or he doesn't use the word narrow, but the common wisdom I filter out from all the reading is this filter, the band, the useful band there is from about 1 to 16 hertz with a peak at 4 hertz. But I don't know what to say further. Most of the paper 1 to 16, peak at 4. Why is so? Of course, people say, oh, I know, because 4 hertz is like a syllabic rate. But that's more like hand waving. We're not talking about syllables here. We are talking of speech. I don't know where syllables are. But 1 to 16. And Rasta filter of Hynek actually went down from 4 down to 0 to about 0.1. And why low frequencies remove them? Why are they important? Oh, I have the picture. You see, this is the Rasta filter. You can see it is peak at about 4, goes down to very low values, and then it goes down to 16 hertz, also low values. So now, what is the filter? I'll go back to my view graph. How do you relate all this to what I said? I have only, NST-FT, I have only 1 filter through which I look. I don't have subband filter and that filter. And I am questioning, why do we have all these filters? If I want to look at a small part of the spectrum or frequency range, I just put 1 filter the way I have it, because that you look at as closely as you like. If I want to look at 1 hertz bandwidth, you can make that filter 1 second wide or whatever it is. If I want to look at 10 hertz, I can make so wide, and so on, so on. So I need only 1 filter. I don't know what I have, the next one which may show. Yeah. So if you come there, to reiterate what I said, there's only 1 filter. If I want to look the speech frequencies through a narrow filter, I specify what narrow filter. I have to specify what shape and how wide, and that's all I use. I don't need several filters. 1 filter which will first divide a speech spectrum into 16 band or 20 band, and another filter which will take 1 second. Why all this complication? And that was my question. I would like to hear from Hynek if he has some insights.
Just started with the short-term spectrum and then we are fixing it.
That is right, that I can see. But we could have started like this. And this picture is not mine, it is an old picture. It is in Carlos' thesis, and it is in fact, this picture started with Jim Flanagan's work on phase vocoder. And he got several MIT co-op working on that topic. And they produced a lot of this, but their interest was different vocoders, so they didn't pay much attention to many of these things what I'm discussing. But this is how it is. So the demodulation model of STFT has a filter, but that is a straightforward question. How narrow I should look at? Should I look at 1 Hertz width? But if I look at 1 Hertz width, and if I have a 10,000 Hertz signal, I have to have 10,000 frequency samples. And people will hate me. Oh, we can't do 10,000. Well, that's not beside the point. Computers are becoming bigger and bigger. Our knowledge is becoming better and better. 10,000 is not a very large number. On top of it, and, I think I mentioned at OGI once, that a large dimensional space is a better space to work because the distances there are much better defined than a small space, because the points get clustered in a very high dimensional space. And your normal distribution will require too much work. If you go a million dimensional space, it will be almost like a delta function. So life will be simpler to model. But that's beside the point. So but question is, should I use 1 Hertz, 2 Hertz, 4 Hertz, 10 Hertz, 20 Hertz, more? What's the point? If you use narrower bandwidth, then this microstructure is simpler in some sense because not too many things happen. Time variation will be smoother. The bandwidth exactly is known. If I have let's take example now in this case, a 1 second filter. A 1 second filter has a very small bandwidth of variation. It's half a second, 2 seconds, and 4 seconds, a few seconds bandwidth. So not many things. It's really very smooth variation if you see the output of that. Now, I said I was tempted to do this, the filtering operation which Hynek did on the magnitude square. Of course, you get a lot of other things, but this is a trivial operation on ST of omega. Where is this? ST of omega. If I take to convert to modulation frequency theta, just like Hynek did, nothing to worry, nothing to think about. You get the same original speech Fourier transform. With a shift. Of course they should get with a shift because I have shifted by omega, it will shift it by omega. That's about it. Nothing new, nothing great. And h of theta is because at the window, it will multiply that because it's a convolution and it's straightforward. So there's not much to learn here in modulation. So I got rid of modulation thinking from my head. So less thing to worry about. So I have only two things. I have a speech signal I want to worry about. I have a frequency called omega, and I want to worry about it. What should be the frequency omega? How often I should do it? Should I have a linear scale or on some kind of a perceptual scale? We can all discuss that, and there could be true. How often it should be, that depends upon the width of linear filter. Otherwise, I'll have holes in my analysis. And the other variable is this filter h of t, how long it should be, what kind of shape it should be, symmetrical, anti-symmetrical, how sharp the cutoff should be on both sides. And these questions are the question I am struggling. And that's why I came to talk here, to get your input on that part. Now, I'll give you just one example of, now I looked at short time Fourier component. Generally, I don't see pictures, and I shall let me look. I'll only look at magnitude squared in the papers. But I thought I would look at that. And it has phenomena which I am trying to still learn. What is this going on? Jiggle-miggle here. A little here, little there. But it is directly the waveform in some sense. It's a shifted waveform, and there's nothing more to it. It's a very transparent representation. And I will find answer to this ups and downs here. It is some effect which I don't know right now. But I just took 4 samples, and it's a word bungalow, for example, or something. And this is the sine. Now the question will come very soon. This is the cosine and this is the sine. Now we have 2 components. Short time Fourier transform is not a real number, it's a complex. I was worrying about that. And you have to worry, what do you do with this? People say phase immediately. Oh, why are you doing that? We don't hear phase. But this is not a good statement to make. Phase is a complicated thing. Phase as a function of time becomes frequency, d phi by dt. D phi by d omega becomes group delay, and it has different meanings. And if you put a lot of d phi by d omega, you will get reverberation. If you put a lot of d phi by dt, you can change the frequency and you get a new signal. So phase is not something which you can take casually and play around. The phase of I am talking here over short time periods, like a second, doesn't change much. It's like a complex constant. And taking care of phase is worrying about a complex constant. So if I'm comparing two sequences, one set of Fourier transform under one condition and another set of conditions, I know there is a e to the power j phi missing there, right? Arbitrary, hanging along there, but not a problem. I can correlate those quantities and e j phi will disappear. And correlations, as you know, correlations in central linear scale factor. E to the power j phi is a scale factor over short period of time. And it's not a major problem. So L was worried. I would like to hear his worries.
No, because I only saw a real number. When you said here's the cosine, I was happy.
Yeah. So complex number has a little problem, but I don't think it is as much of a problem as magnitude squared has. Okay. And I was asked about the windows. I think by now it's clear. I am talking of only one window, which is put on the speech signal, but I don't even call window. I call it a filter. I'm looking at the speech signal through a little microscope and trying to see in detail what's happening. And there's the question, how much detail I should look the speech signal into and as a function of frequencies, and maybe there are hidden treasures there, which we have not seen.
It depends on what you're trying to do with it, right?
That is right. But one application could be recognizing of sounds.
Right, but for even then, I mean, the answer is going to be different depending on,
What sound you are talking about?
yeah, or what version of performance you want. If you want to know, if you want to recognize uniformly across the entire collection of possible sounds, then you give one answer, and if you want to get better performance in some region, then perhaps a different.
So that's exactly right. So now the question comes, should we use only one window or several windows? And multi-tapered windows have been discussed in literature, and they have advantages, but in different contexts. Our mathematics department and Bell Labs did some work on this. And they were saying use multi-tapered windows. That means don't have one h of t, use several h of t's. Because some h of t may work on some particular sound, and some h of t may work on some other sound. Now we have a little more problem, but nothing very, very kind of difficult conceptually. And practically, I have to do experiments to determine which h of t is relevant for which kind of sound.
Right, but you're going to do multiple h of t's.
Multiple, but maybe I will find out that some h of t are good for stops, some h of t are good for long sounds, and I don't know, but we need now new experiments. Moreover, the shape, I cannot take my wisdom from old work of using magnitude squared, but magnitude squared has a lot of trash sitting there. I don't know, they may be removing all the trash rather than doing some useful filtering. And I'm nothing negative, but magnitude squared has this problem. It has a lot of unwanted things which come out of nowhere, and then I have to do a filtering to get rid of them. Why to put them there? So if I do experiment, I will do directly on STFT and start seeing what the effect of window is. So it opens the door for a large number of experiments of psychoacoustics to figure out.
Well, I guess it all depends if you believe in a linear model of speech production or if you don't believe.
That's not linear. Speech production is not linear.
Because I think it's dangerous to just deal with the speech signal as such, because it comes from somewhere. It comes from the vocal tract. And I know what is the modulating function, and I know what is the carrier. Basically. Right? But maybe, I don't know where you're going. Maybe you'll get somewhere with this. But the reason why we got into power spectrum, say, well, okay, and logarithm of that, we say we want to be additive. Somewhere there is a excitation, there is a modulating part. There is a vocal tract, there is a source. And we are dealing with vocal tract. That was the thinking. I mean, since you asked, like, why we got into it. what we got into. But I agree with you that you get a mess if you get a correlated signals. But if you,
2 signals or 3 or add. But Homer Dudley had a discrimination. I had to read this. Why did he want to filter back analysis? Think of it, first there were no computers those days. He had filters were available, and he had the idea to go into real demodulation. But he said, as an approximation, I will take the output of filters passed through rectifiers and smooth out as a approximation, and I will go along with that. Because in 1928, to do anything more will be impossible. But think of it. First, speech production is not linear. There is no justification for magnitude squared based on any model of speech production. It's a convolution. If you believe in that, if you take to Jim Kaiser, he will do something else. There are a lot of things going on, but speech production is a complex thing. The simplest model is linear model of convolution, but that doesn't say anything because convolution becomes multiplication both for STFT and also as for the spectrum. So I have no problem. But the magnitude squared has this problem. When you have noise added, it creates tremendously superfluous component. If you have reverberation, more trouble. And if you have 2 or 3 voices coming in here, if you add speech and music, problems. And they are not correlated signals. Speech and music are uncorrelated, but that doesn't matter because over a short time period, they will create interference. And you have to resolve them if you want to recognize a speech in presence of music. Yes?
Slightly off topic, but since we're talking about phase, it occurred to me that there's this interesting result in vision where you take an image and do its Fourier transform, and you just make the magnitude uniform and just reconstruct it from the phase, and you can still see the picture. If you do the same thing by making the phase uniform, construct from magnitude, you don't see anything. Is there any kind of similar result in speech? Or
There are two results here. One is one result was discussed by Oppenheim. One of his students did the thesis there. Question came: if I only know phase of a time sequence, can I create the waveform? We don't know the magnitude, only the phase. And he gave a reconstruction algorithm, or his student gave. Basically, if the function can be expressed as a Fourier series, which we said, what's the problem? We can always do that. That's a constraint. Then you have only unknowns, which are number of amplitude coefficients, but you are given the signal now at certain instant of time, and which are time is known, but and it's solving a set of linear equations, which then gives you the waveform as a set of Fourier coefficients going through multiplying a cosine and sine, and that works. So the early in 60s, or no, yeah, late 60s, I heard number of papers. People said, look, I have a windowed signal of time t. I will take its magnitude squared, and from that I will reconstruct the signal. Simply the fact that the signal is time limited, this gives you exact reconstruction because all the phases will smear out. So given the constraint is within time t, is enough to fix the problem. It's not a stable inversion, simply because the small changes will give you a lot of multiple solutions. So I don't know to what extent the constraint of the picture help you out there in all this, but the phase and magnitude squared are still phenomena not well understood in speech.
if I may comment,
Yeah.
it all depends on the length of your window indeed. If you take 5-second window, I can guarantee you that phase is much more important even in speech than magnitude. Equalize magnitude, all you are doing, you are filtering your speech through a fixed filter. It's okay. It will not sound the same, but you will understand. You take 10 millisecond window, you can throw away phase. People have done it many times, right? You put in random phase, minimum phase, maximum phase, whatever, all you understand it all. So it depends indeed what Bishnu is addressing here, the length of the window. And in the image, you're looking over the whole image. Sure. Phase is much more powerful.
Now, I read also a paper by Kuldeep Paliwal. His method, I cannot identify completely what he did. It's little, not going to depth, but what he did was he took the phase from the short time Fourier transform, magnitude, then threw away the amplitude square term and kept the phase. From the phase, he recreated a speech signal which he put through a speech recognizer. And some of his papers suggest he gets a reasonable score, but I don't know to what extent all this is sound work. Other questions or comments?
How does the ear do it?
Very good question, Jim. We don't know. We don't know who.
We know something, right? There is a one-way rectification.
Yeah, even that question is very.
There is one-way rectification right on auditory nerve.
But you see, I'll tell you, I'm not criticizing you on this. See, with the first work I did in speech, I produced a two-level signal and reconstructed very high-quality speech of that. So someone may say you only need two levels to recreate. I was predicting a speech and quantizing difference in the feedback loop, and here comes the output. So if someone observed me, oh, in the transition line you're sending two-level signal. Oh, for a speech only I need two levels. That's wrong. We need 8-bit code there. One has to examine in detail the entire operation of a device. Sigma delta mod is another example. You sample high enough, delta mod 1 two-level signal produces as high quality as you like by sampling. Now in the auditory domain, it's all open to question how much sampling in the frequency domain or basilar membrane they are doing, and plus is there any feedback in the whole system. And each time I talk to Odette, we get lost because Odette gives us my reference point for hearing, and he says that there may be feedback. So I give up. I don't know. One cannot observe a part of any hardware and draw big conclusions about the entire function. So it's not criticism of what you are saying, but this is, so I don't want to go further into that conclusion. People say, yeah, with half-wave rectification, ear can reconstruct the entire thing if it is using some mechanics similar to, signal processing is very powerful in that sense. And that, Jim, partially answers to understand the complete mechanics. People are, I heard something that people are doing measurements on human brains and getting a lot of information about the transfer functions. So one day we may have a picture which is closer to reality than we have today.
Well, a simpler question there or comment, since one day we'll have a better idea, but we don't yet. As just a humble statistician, you were talking about doing the experiments, doing lots of experiments in order to determine what the best filters are for particular problems. And that's clearly much easier if we think about the design of experiments problem. It's much easier in your scenario, in the linear scenario, because one can design experiments where you get more information between the experiments than you can ever do when you're using.
Also, I can go back to the original signal trivially.
Yeah,
if I do a modification of short time Fourier component, I can add them together. I get the speech signal. I can hear, oh, what have I done?
That's right.
Right? So that's much easier. And I like that because you can go back and forth as the way you like it. Well, if there are no further questions, I am at the limit of my talk. I think there is no other view graph. Let me see. Oh, I just wanted to show, if you take the magnitude square power spectrum, I just did a 200 millisecond window, and it's awfully complicated story here. A lot of things are going on. We cannot just smooth it and say life is easy. Life is complicated there. And what part of complication is my own creation and what is inherently in the signal is a big issue. Okay, thank you very much for listening and your comments and your wisdom. I'll keep this in mind.
Any questions?
More? Oh, absolutely.
Supposing you have a multitude of windows combined with time and frequency history, we're kind of getting into your very high-dimensional space that you alluded to. Do you have any speculation on what to do then? What to do in the high-dimensional space?
No, I have no speculation, but I did some work. And about high dimensional, I got interested when I was working at AT&T Labs into this question of why did I get interested in that? You see, I have switched my interest from speech coding to speech recognition, not as a profound researcher, because AT&T Labs was full of experts. So I told Larry, keep me alone there. I am like a 8th grade student now in speech recognition, so I had to learn about that. So they were gracious enough to leave me 5 years alone and said, think. So no one asked me any question, no report, no justification. So the question which you kind of started, since I was completely free, the question which kind of started is access into any information database. I was really amazed that I am here and somebody calls me and says, do you remember me? I was your high school classmate. I close my eyes and say, oh, yes. Now, I have a lot of information stored there. I don't know what the capacity of human brain is, but within a few seconds, I'm able to access it. So I get interested in accessing large databases quickly. And to tell Larry that I am working on speech recognition, I said speech recognition is an access problem. You speak, you create a code in acoustic side which gives you a pointer in your brain to the right place where phoneme information is there, and all these things are linked. Not only one phoneme, it's who spoke, under what context. So there's an associative memory where all these different things are stored there. So when you speak, immediately our neural networks point to a particular place, but how exactly? Because the speech information is very fuzzy. Acoustics is different, you speak differently, I speak differently. How come it can go to one point? So that brought me to studies which said in extremely high dimensional space, higher dimension you go to, the imprecision about location of a point becomes smaller and smaller. And that is nothing very deep. There are enough work done to see that in a high dimensional space, the probability of error if you want to identify Gaussian distribution will go smaller and smaller, and it has the mathematics similar to mathematics of channel capacity of channel theorem. But in a high dimensional space, you can decode with errors. So our memory is, since you go to exact space, only thing we have to store is a mapping of that location into the acoustic imperfect signal. So a signal comes, it maps to almost the right space. Now, I thought that would be interesting. I haven't done anything recently on that, but I have it in mind. Once I resolve all these issues, and if I have to use a high dimensional space, I would like to see how that information can be put to work. I think high dimensionality is our friend.
LDA and putting it right back down into low.
Yeah, that's the conventional wisdom. But I feel high dimension is nothing to be frightened with. It's good because only in a very high dimensional space we can decode with large amount of uncertainty with a small amount of error.
So I might have missed your talk because I came late a little bit because I got stuck in traffic. So the thing is, if usually like LDA or any kind of dimensional reduction approaches are used in case of multitude of windows to get rid of the correlation. So do you think that correlation information, like correlation of information of one window as with respect to the others, are they helpful, or do you think that might create a problem in terms of ASR?
You see, if the distribution is non-spherical, certainly we can make it spherical. I have no problem by using any one of the techniques. There are enough methods available to rotate the eigenvectors to come in the right way. So that's not a problem. So you will get not a set of independent variables, but a set of orthogonal variables. Singular value decomposition is one way, but you say principal component analysis is one way. All are the same thing. You take a covariance matrix, find its eigenvectors, eigenvalues, and just multiply, and you get it. But that's not the fundamental issue. If you have a very large number of dimensions, you may be right in saying, how am I going to handle these large covariance matrices, right? And there is an open question. If you have a high dimensional space with largely uncorrelated variables, it's not difficult to handle. If we have very large dimensional spaces with a high amount of correlation is a problem, but then I see there's a lot of literature. There's the topic of searching in high dimensional spaces an active topic. It comes from many other sources. You have documents, literature, you want to search, how quickly you can search. And one operation people done it, they project a very high dimensional space into a smaller space by random projections. And some of the results show the random projections in a smaller space, not by this other analysis, by random projection, is still is a reasonable choice. I don't know to what extent it's choice for speech or not. I don't know. I haven't done any work. I just read some papers on this. So random projections is another, somebody remarked today, there is some work done on that, and I think you should comment on that. I only know, like in compressed sensing, which is another interesting topic, because that deals with the sparse things. And compressed sensing is getting more attention. There will be IEEE issue on that and all that. And they take random projection on the original space and then do this, but please answer, you say.
Well, it's the same. The connection has been established. So random projection is a sense of compressed sensing. So that's pretty well known in the compressed sensing community. However, my question is related to, can we learn something from the compression community? So for example, we do MP3 for coding or AAC coding. It's not using short time Fourier transform. It's using MPCT, that's modulated lab transform filter banks. And the way the optimal compression is being achieved by switching from long window to short window adaptively. The code decides that. We don't have to control. Okay, so the code basically you have two choices. You try the long one, you try the short one, whoever comes out with the lower bit stream, lower bit rate, or sparser representation wins. And you encode the mode, you encode so I wonder, is there anything that we can do here of similar natures? You can try many choices and automatically pick the sparser or the sparsest, whatever, best representations that you like and declare that's the winner.
It's possible. One issue which I think is the back of my mind is if you have multiple signals added together, right? Suppose take two for a simple example. I want to sort out. So if I look at the STFT of the sum signal, and in the time frequency plane, each signal may have a simpler distribution of TF, lot of holes, few things. You add together, it has much more confusion. There may be a way to ask this question, can I decompose S1 plus S2 into S1 and S2 such that each time frequency distribution is of a simpler nature, maybe less entropy maybe, or something like that. That may be a possibility. Now, usually I didn't say that. Behind all the work in speech, that we have a sparse signal. If a speech information was dense, compression will not work, recognition will not work, life will be tough. So assume it is sparse, and then it comes to a more difficult question, which I kind of trying to learn. I use least squares not because I know it's right. Least squares put a lot of garbage into some small things, because I can take d by dt. d by d of something, differentiate, get a linear equation. That was convenience. I feel we should use norm L1 and below. The fractional norm like L half, L1 third have their own advantages. But in the mathematics is different there, so we keep out of that. But it's our job to learn that. And we will find that for sparse representation, norms less than half, L half, are more appropriate.
So the compressed sensing people say that L0 is the best.
Yeah, L0 is going a little too far.
But then that's a little too far. So
The
so
math
they
of
back up, right? They back up and they say,
but
okay.
math of L0 is
let's
simpler
try
to
L1
understand.
as a start, and then we worry about a half and a third later on.
Yeah, no, but L0 is simpler to deal with in terms of looking at equations and all that. But I think we should look at L1 third.
But less than L1 norms roll out with convex.
Yeah,
Yeah.
that's. Yeah,
But that doesn't matter.
Yeah, if it's right, that doesn't. If it's right, that doesn't matter. I mean, it matters.
No, I mean the L2 norm is like looking for your keys under the street light, right? Because that's where the light is. Even if you lost your
No,
keys.
it takes a lot of things, square them and buries them there.
Well, if there are lots of keys scattered around, you don't have a key file.
trash can.
That's
is
a
nearby.
The expected number of keys that you'll be able to see is greater. But if you're looking for a particular key, you gotta look where it is.
I'm still thinking about this thing, because I think, Vishnu, that you, of course, worry about these product terms and this sort of thing, because you are a speech coding person. You want to reconstruct the speech somewhere back in your mind. I think that is maybe...
No, I want to separate. I think we are going to add with additive signals where is, all the applications. I can't talk on a cell phone by saying, quiet. I am only speaking, nobody talks. When I get all these signals, what do I do?
If I am a recognition person,
Yeah.
and I have two sources, F1 and 2,
Yeah.
and they mix together, what's the big deal? As long as they carry both of them with the information I'm interested in, it doesn't really bother me, right?
No, they interfere with each other
Well,
in terms of
they interfere,
addition,
but they
because
interfere in a predictable way somehow. If, of course, you have a problem, as you correctly pointed out, if you have somehow correlated sources and you want to separate them.
two persons talking plus some noise, street noise and
but
a
you
car
hope the
going.
voices are correlated.
Yeah,
You hope.
but not on short time frames. That's not true. You get cross terms. Yeah, well, Hinek, you have to think about it. My feeling is, in practical speech, where speech and music is one example, we have no problem. We enjoy a person singing and some music going on. Well, that should be not a challenge, but it will create problems of enormous nature if you want to recognize that. Don't call noise, the music as noise, because that disturbs everything. To make proper models of all these uncertain additions of the signal creates enormous. No, it could be. I have seen a lot of papers where people are trying to invert all this crosstalk and all this. So maybe a possibility there, in fact, that people have some signal processing to get out of that. I don't deny that. But at this moment, I found this too complex. To take one more baggage, I already have trouble this. And this still doesn't say that I should take a Fourier transform in two windows. I still can, even without magnitude squared, I will do magnitude squared right away after one window. Why two windows? Why two set of filters and one more window? So that's unnecessary complication.
But what is the problem then with the old Dudley's approach? Like when you find a carrier, find a modulating function. Modulating function is interesting. Carrier, we put a noise in or whatever pulses. It sounds terrible, but clearly the modulation is the one which carries the information. You can listen to it. You're excited by noise. You listen to it. You understand everything perfectly okay, as I was telling you today.
Not completely true. Less on this.
But it's okay, right? You know that information is there.
We are working on that kind of thing. We do coherent demodulation, not magnitude squared. and that branch is going, but we are still struggling with how to find the carrier. We have tried so many things, so many theses has come, but solution is not there.
True, but you still are after reconstructing. That may be my point.
No, in this case, not me.
We are speech recognition.
No,
we recognize, we don't recognize.
Atlas's problems are like that. He wants to clean the noise, he wants to separate the sounds. No, but my interest was, if I want to recognize practical speech, it has always so many things going on.
So I have a colleague who would be very sympathetic to this point of view, and I think you're really onto something. The next thing that he always says when he talks like this is that speech recognition models with hidden Markov models and Gaussian mixture models are basically the way that speech recognizers deal with all this garbage that gets introduced by sort of the kind of traditional signal processing that introduces all these sort of artifacts. And I wonder if you share sort of his intuition that if we did a better job sort of in the signal processing, then we could use much simpler models.
Yeah, it's a controversial thing. What happens is that certainly the hidden Markov model is a legitimate way of taking care of uncertain noise elements there. We don't have to model them. But if they have a structured signal added to treat that like noise, added some more complexity, and there's a price to pay because you have to learn all these things. A structured noise should be dealt with a structured noise, and music is not even a structured noise. Music is pure, nice, beautiful signal. So I think we can still use HMM, but we have to first kind of separate out some of these interfering signals. Thank you very much.
I would like to welcome among us Dr. Bishnu Atal. I was thinking how to introduce him because if I were just naming all the awards which he got, I think that we would cut into his talk significantly. But he has the usual honors, Academy of Sciences, Academy of Engineering, Inventors Hall of Fame, and so on and so on. But I realized that probably the best introduction is that you realize that most of us actually carry a little bit of Bishnu in our pockets. Because if you take out your cell phone, I can guarantee you that a little bit of Bishnu is in each of these cell phones, namely linear prediction of speech, which now looks like a normal thing, just like Fourier transform and whatever. But when it was invented some 30 years ago, 40 years ago, 30 years ago, it wasn't.
He's not old enough to have done
Yeah, it wasn't as obvious as it looks to us right now. And Bishnu got on the other things too. I mean, and he will tell us about that today. So please, Dr. Bishnu Atal.
And thank you, Hinek. I am very glad and I am really grateful for the university and the speech group here to invite me. When Hinek wrote to me that I should give a seminar here, I was thinking, well, who will go all the way from state of Washington to Maryland? But then I said I should learn more about the work being done here, and he is here. That is kind of a surprise because he was supposed to be in Switzerland. And I don't know how he landed up here, so I thought I will find out what he is doing there. On top of it, I was struggling with some problems in Fourier analysis, and I thought, that's it. Where else I can get so much help? You know, I don't work at Bell Labs anymore, and for every little thing I have to run around. And here at one place, all the knowledge is here. So I'm going to talk about this topic, which is an old topic, and you wonder what is this Fourier analysis business going on? Why are you working on this topic? What is this long settled thing? It's no longer an issue, anything. And probably this is true. You know, when I joined Bell Lab in 1961, Fourier analysis was a hot topic then. Blackman and Tukey had just published their monograph in BSTJ in '58. And Fourier analysis was not a thing which was common. It used to be very expensive to do any Fourier analysis. Computers were just coming, they were slow, and Fourier analysis takes a long time to compute. But when Blackman and Tukey did some Fourier analysis on a length, not on a speech, but on some data from AT&T, they found a lot of unwanted phenomena there, because Fourier transforms are defined on a long record of what I call infinite length. But we live in real world where nothing is infinite, and if you have a finite record, no matter how long it is, it creates problem if you do a Fourier analysis, due to minus t to plus t doesn't do things right. And a lot of other problems. If you ever put white noise into this integral, all more problems come in. So they put their wisdom in. They said we should use tapered windows. They discussed number of windows, and Hamming window was one of them. And it became Hamming window became